Hello and welcome to this manufacturing process technology part 2 module 23. We were discussing about how the heating effects jeopardize the ECM process and how you can design the optimum flow velocity so that the heat transfer across the electrodes goes out and the electrolyte never reaches the boiling point. Today we are going to do a little bit different aspect of the ECM, which is obviously that one part is that when the heating increases there is an electrolyte boiling, but there is a very important secondary aspect about even hydrogen bubble generation that changes the conductivity drastically of an ECM setup, and therefore there are changes related to machining rates because obviously the conductivity is different based on wherever these hydrogen bubbles are generated. As you know, hydrogen is generated as a result of the formation of FeOH from the workpiece and into the solution. So in the whole mathematical analysis so far, the different parameters and properties were assumed to be uniform throughout the face of the electrode. We never assumed the conductivity to be varying, or for example the other parameters like, let's say, temperature, etc., to be varying quite a bit. Okay, so a variation in these properties except the machining processes. So therefore, supposing if I were to tell you that hydrogen is getting generated the moment the electrolyte enters between the two electrode workpiece, and as the electrolyte goes ahead, hydrogen keeps on adding and the concentration keeps on increasing. So obviously there is going to be a gradient in the hydrogen concentration and a gradient in the conductivity because of such processes. So obviously the electrolyte conductivity changes as the electrolyte passes along the gap owing to increase in the electrolyte temperature, the evolution of hydrogen bubbles, and the formation of precipitates. Okay, so this effect is very small in proportion obviously in comparison to the hydrogen. Hydrogen changes conductivity quite a lot. Think of it like this. So this is the tool, workpiece and inter-electrode gap combination, and you are flowing the electrode in this direction. So obviously the hydrogen gas goes on getting generated as the electrolyte goes past, but obviously the concentrations, if we look at in the different zones, let's say C1, C2, C3, C4, C4 is greater than C1, C3 is greater than C2 is greater than C1, obviously because hydrogen is keeping on getting added as the electrolyte is flowing. Okay, so because of the flow of electricity, the electrolyte temperature also gradually would increase. So far we assumed only constancy in the tool phase temperatures or the workpiece phase temperatures when we did the heat analysis, but we never considered the fact that what if the temperature here, for example, of the electrolyte and the temperature here as the electrolyte passes by is quite different from each other. So obviously there are going to be changes in the machining removal rate from this zone all the way to the end zone here, and obviously it will depend on the direction of the electrolyte flow. So the conductivity changes would result finally in a non-uniformity in the current density. Current density, as we know, is proportional to the material removal rate, and so therefore the MRR would get changed substantially in the direction of the electrolyte flow. So I already mentioned about the bubbles and how they are swept by the electrolytes, and the concentration of such bubbles would increase in the direction of the flow. Again, the overall conductivity of the current density would vary along the same direction. So because of such variations, there is always a possibility of the electrode tool surface, the workpiece tool surfaces to get changed substantially because of such variations. And in fact, such electrochemical machining processes would result in n number of issues which are related to the surface finish related to the workpiece surface. So in general, a very good surface finish is desired in parts machined by ECM, and a study of the possibilities that may result in the bad finishing is absolutely important. And obviously, as I told you, these different factors like selective dissolution, sporadic breakdown of the anodic film, and the flow separation and formulation of eddies, and evolution of hydrogen gas would all result into poor surface finish. So one aspect obviously is the overall machining of the workpiece surface based on the direction of the electrolyte flow, and the other aspect is obviously the surface finish related issues which come because of the electrolyte flow. So, let us look at this step by step. First look into the selective dissolution, what we mean by that. So, let us say we are doing alloys, okay, and we are trying to electrochemically machine alloys. So, in different alloys there are different constituents, they have varying electrode potentials, and even in pure metals, if you take there is still a problem that the dissolution potential at the grain boundaries are quite different from those inside the grain. So, the grain boundaries are obviously quite changed in terms of its composition, etc., because of, or even the orientation of the grain growth, etc., because it is really a merging between two different lattices grown in two different directions. Okay, so there are going to be some changes in the aspects which are related to the dissolution process of such boundaries. So, let us consider such an alloyed system where there are two phases A and B, and let us consider that these two constituents are placed in an ECM machine as the workpiece, and B is projected outside by a distance, let us say delta, in comparison to A. So, the potential required for dissolution of the phase A is, let us say, VDA, which is actually given by this region here, right here, and the potential required for dissolution of B in this case is slightly greater, VDB, which is given by this particular line here. So, this is VDB, this is VDA. These are two phases, obviously they have different dissolution potentials, and this is being represented here. So, we would like to presume here that there is an ohmic drop in the electrolyte which is in between this gap. This is all filled by electrolyte, and there is a straight line ohmic drop, as you can see here, right here, as the voltage changes between the cathode and the anode, okay, and it is done in a manner so that the VDA, the available potential is, which would cause the start of the dissolution of the phase A, is available at a surface. But if we look at the availability of VDB potential, it is actually down underneath somewhere where the voltage drop is so that it results in VDB. Okay. So, therefore, the phase B would start dissolving much earlier from probably this point in comparison to the phase A, and therefore, there is a tendency of surface roughness to happen. So, because obviously the B is getting eroded at a much different interelectrode gap in comparison to the phase A. So, A and B would not really rhythm with each other as far as the equipotential surfaces go. So, typically in a pure phase alloy, we estimated in our all calculations that this whole surface is equipotential, and the dissolution would happen, and the you can say the recession of the workpiece would happen as a flat surface. So, in this case it is no longer true anymore, and so there is unevenness due to the difference in the dissolution potentials of the different phases. So, we can see here that in this figure the voltage profile across the gap has been shown, okay, as I mentioned earlier. Dissolution potentials of B and A have been shown as VDB and VDA, and the availability of the VDB at much inside the interelectrode gap region is visible, and VDA only provides the dissolution potential of A at a certain other distance, and so there is always tendency of unevenness to happen between A and B. So, the required potential difference between a point on the surface and the adjacent electrolyte for the ECM to start must be either VDA or VDB, and since the whole anode surface is equipotential and the electrolyte potential varies across the gap as shown, the surface of the grain of B must be projecting away from the surface of the constituent surface A to meet the electrolyte with a lower potential, so that a larger difference VDB is achieved, so that dissolution can start happening. Okay. So, thus in the steady state the work surface will be uneven in general and not very smooth. Obviously, we are working on the differences of potential here, one has to remember, that is the V cathode minus V anode. Okay. That is how the difference comes in this particular case, and therefore, there is a very good reason of why unevenness in the surface should happen, because of the different dissolution potentials VDA and VDB. So, the other interesting issue is that as a function of the interelectrode gap IgE, this roughness would vary still, because it may have to project inwards more or less depending on how steep is the slope. So, if we had a steeper slope of the potential difference between the tool and the workpiece, then obviously you will be able to achieve this VDB much faster in comparison to what it were if the slope was not steeper. So if really the difference between the potential of the work and the tool is more, there may be a different machining rate, and there may be probably a more even surface in comparison to when it were smoother, as in this particular case. So comparing the electric fields, so an approximate expression of the projection height can also be derived. Let's say if we compare both the electric fields in this case, so we have some potential V minus VDA by Y as the electric field which is there from the surface A all the way to the tool surface. Let us assume the V to be the anode potential in this particular case, and this becomes equal to V minus VDB by Y minus delta. Obviously we know that a greater voltage would be needed, or a greater dissolution potential would be needed for the phase B in this particular case. Okay, but the electric fields are same. Electric fields are parallel and they are quite same, except some curling which happens at these corners and this corners. Okay, but otherwise they are more or less same based on what is the voltage per unit distance. So therefore from this expression we can find out the value of delta as 1 minus V minus VDB by V minus VDA times of Y. Okay, and this is basically the difference of heights between both phases as we do electrochemical machining. So it gives you a ballpark idea more or less of the overall average surface roughness due to this. The other criteria for causing poor surface finishes, the sporadic breakdown of the anodic film. Let us see what we mean by this. So the main reason for the sporadic breakdown of the anodic film is the gradual fall in the potential difference between the work surface and the electrolyte in a region away from the machining zone. Let us say this is the machining zone and we are talking about this region away from the machining zone. So obviously, as you know, the electric field between the tool and the workpiece would fall down as a function as a square of the distance as it goes from this particular point all the way onwards, and therefore the field overall that is available here or here or here would vary quite a bit, and the field would be lesser and lesser as we go ahead. You have to remember that there is electrolyte flow in this region where we are considering this field to sort of go out. So the electrolyte is traveling all the way over this work surface into these regions, and probably you can say that a field is being created between the tool and work by virtue of the electrolyte flow over these regions. So obviously there is a variation in the surface potential of the anode because the electric fields are different in different points away from the tool workpiece zone, and here till the point P1 the potential is enough to cause dissolution of all the phases. But if we consider an alloy and if we consider many phases to be present, which is normally the case because you don't have control on the impurities to an extent of and obviously steel itself is an alloy of carbon and iron. So therefore there is a chance that up to potential P1 everything is dissolving, but beyond that when the electrolyte flow happens and the electric field dips down, there is a tendency of selective dissolution to happen. So all phases which are having lower potentials than the, let's say, the maximum dissolution potential phase would start coming off, and therefore beyond P1 the anode surface potential would sort of drop down to an effect that an increasing number of phases would stop dissolving, resulting in a uneven surface away from the tool electrolyte zone. So even if we are machining in this zone, we need to be concerned about the overall surface finish of the component because the electrolyte flows into this region. So one of the ways to stop this from happening is to sort of guard the electrolyte flow from flowing out of the tool electrode gap or the inter-electrode gap, and this could be done by probably guiding the electrolyte only in the machining zone and not beyond. But the question is, there is always going to be leakages and there are going to be aspects related to the such phase dissolution of workpiece when we talk about ECM. So ultimately when only a few phases remain active and dissolve, a concentration of the electric field results since the active phases occupy a portion of the anode surface, and if you have small points and crevices coming off in these particular regions, there is always a tendency of field concentration to happen, which would cause these phases to dissolve very rapidly, and therefore it would start forming pits in these regions, which would be related to the surface finish. So obviously beyond P2 point, the field is no longer effective. It falls to such a low value that there is no dissolution which takes place, and so immediately around the vicinity of the machined zone, there is this formation of the sporadic breakdown regions where there are small pits which are observed at the end of the ECM process. The other major cause of improper surface finish in an ECM is given by this flow separation and formation of eddies. So eddies are basically local recirculation zones which are formulated very near the surface because of such selective dissolution and such corners and crevices, which result in any event the electrolyte flow is quite slow and quite laminar in nature because of the IEG being very small, and so therefore obviously you can also think of it that in this manner, that as the electrolyte exits out of the interelectrode gap, there is really no guiding, and there is a sort of a surface spreading of the electrolyte, you could say, over that particular region, and the presence of hills and valleys on the anode surface because of such dissolutions cause a separation of the electrolyte flow and eddy formation. So let us say, for example, if the electrolyte from this particular machining zone is flowing ahead, and let me just draw it a little appropriately. So this is the machined zone, and let us say these are the regions where such the breakdowns are happening. So obviously as the electrolyte is flowing here and it is flowing with some small velocity, there is a tendency of recirculating zones to get formulated, or eddies to get formulated over these regions. So in these eddies, which are separated from the main stream, the only problem which happens is that the concentration of the metal ion starts increasing, and there is a very large concentration of the metal ion, because obviously metal ions are going to dissolve in the electrolyte in the presence of a field. So this results in a high concentration over potential in the eddies and introduces localized variations in the removal rates, consequently an uneven surface finish in these regions of the surfaces. So even if the eddies are present somewhere in the machining zone, this is going to be a main problem. So apart from the presence of hills and valleys, the flow separation may also be causing an important, may be caused by an improper design of the tooling system and the electrolyte flow path, and so there may be the need of quite a bit of care for a designer to design the flow direction and the flow path of an electrolyte in a manner so that such problems don't happen. The other issue related to the surface finish is the evolution of hydrogen gas. I think I had earlier already illustrated how important it is that the concentration of the hydrogen gas and variation therein results in a lot of material removal issues or non-uniformities across the interelectrode gap. Just a recall that the hydrogen starts coming out the moment the dissolution starts happening from the workpiece side to the tool side. In this case, let us say this is the tool, this is the workpiece, and the arrows show the flow direction. So the hydrogen keeps on oozing out and bubbling out, and so the idea is that the concentrations in this zone and this zone and this zone are quite different. C3 is obviously more than C2 is obviously more than C1 because hydrogen keeps on adding to the in the flow direction of the electrolyte. So this presence of hydrogen in the electrolyte reduces the specific conductivity of the solution quite a bit, and so the material removal rate, which is affected by the current density factor, which is again dependent on the conductivity of the solution, would be greatly jeopardized because of such packing up of hydrogen gas within the electrolyte in the flow direction. So this effect increases downstream with an increase in the hydrogen gas concentration, resulting in an overall deterioration of the surface finish, and therefore it is very important for a ECM machinist to have a good idea of how to do the tool design. So one of the issues that I have discussed earlier is that the ECM is a process which can be also better known as a die sinking process, where the exact shape of the die and the negative imprint therein would be able to get accumulated on the surface which we are working on. So there are two major aspects of such tool design. One is determining the tool shape so that the desired shape of the job is achieved for given machining condition, and another is designing the tool for considerations other than the overall tool shape, and one of them is obviously the electrolyte flow. I had shown various reasons therein of why surface finish can be jeopardized because of many processes like selective breakdown, selective dissolution, or sporadic breakdown of the anodic film, or hydrogen gas accumulation and change in specific conductivity there, or eddies or vortices or flow separation, which results in all sort of surface finish problems. So we will first look at the first condition here, which is determining the tool shape so that the desired shape of the job can be achieved. And in context of that, I would like to sort of have a little bit theoretical determination of the tool shape, okay, particularly in the case of ECM process. So when a desired shape of the machined workpiece surface is known, it is possible to theoretically determine the required geometry on the tool surface, which will cause this desired shape of the component or the design which has been planned earlier for the component to be executed for a given set of machining conditions. So let the applied potential, the over voltage and the feed rate be given by V delta V and F respectively in this particular case. The equilibrium gap between the anode and cathode surfaces can be expressed as G dash equals K times of V minus delta V divided by rho Z times of F times of small f cos theta, where theta is the direction of inclination to the feed direction of the tool with respect to the workpiece. So here obviously the capital F here is the Faraday constant, the Z is the total dissolvable valency, K is the specific conductivity of the fluid, A is the atomic weight, V obviously is the voltage, delta V is the over voltage potential, D is rho is the density of the phase that is removed, and small f is the feed rate in a direction theta with respect to the surface normal of the workpiece. Okay. So I would like to first select the let's say the situation. You have a xy coordinate system as shown here, and you have a surface which is to be determined. Okay, so this is the tool surface which needs to be determined. The workpiece surface obviously is known to us from the design, and further the feed direction F is really at an angle which is closing the equilibrium gap between the workpiece and the tool at inclination direction theta. Okay, so this really is theta that we are talking about, and let's assume this to be the work, the tool, and further the tool shape which is shown here, right here, is estimated on the basis of the work shape, which comes from the design requirements. Okay, so this really is the component design requirement which has been given. You already know what you have to machine through ECM process, and let us assume that there is a functional relationship y equal to phi x, which is followed by a two-dimensional curve which is a representative of the surface. So we are only doing a 2D analysis here, okay. But obviously this can be extended to 3D. We'll probably try and solve one example where we'll do it in 3D as well. So the coordinates x and y are so selected that the y axis and the feed direction are parallel. Let us consider a 2D case with no variation in the z direction. So the work surface geometry in this particular case is given by a functional relationship y equal to some phi of x. Further, let us assume a point P here in the workpiece, which we know as PW. W stands for work, and the coordinates therein are known to be xw, yw. Okay. So we want to predict what is the corresponding point on the tool and the coordinate therein and the relationship between the same. So let us say the corresponding point on the tool, which is a reflection of the PW here, we call this PT, okay, be represented by coordinates at xt, yt. So the whole goal here is that can I from the xw, yw, which is known to me from this functional relationship y equal to phi x, be able to predict the point PT, which has a coordinates xt, set of coordinates xt and yt. And so the idea would be to develop a similar functional relationship on the tool side, provided the functional relationship on the workpiece side is known to you through design. So having said that, let us look into the condition when a steady state is reached. So let us say when a steady state is reached, the gap between a point on the work surface, also given by PW, xw, yw, and a point on the tool surface given by PT, xt, yt, can be done in a manner that our this PT, PW should be equal to the equilibrium gap GE. And obviously then if I look at these coordinates, yw minus yt, which is actually represented by these two coordinates, okay, these two coordinates yw, yt, similarly xw or xt. So this is xt, this is xw, okay. So yw minus yt is given by PW PT distance cosine of theta, okay. This is the PW PT distance. In other words, if I consider this to be the equilibrium gap GE, we have G cos theta. In a similar manner, I can write xt minus xw, as can be seen here. Xt is greater than xw, okay. The x direction can be represented as PW PT sine of theta, that is G sine of theta. So, we will try to do something in the next module where we will try to see if there is a relation which exists between the knowns which are xw, yw in this case, and the functional relationship there, and the xt, yt where a relationship has to be established. So, with this I would like to close this module, and in the next module let us do the whole tool surface design and try to solve some numerical oriented challenges where you can actually develop from a design requirement of particular component the actual tool shape. So, thank you so much.